Hello all, and thank you for listening to my talk on the vesicularity and rheology of the Kilauea 2018 lava flows. Unfortunately, due to COVID-19, the rheology section of this talk has been curtailed to a later date. This map shows the extent of the Kilauea 2018 lava flow field. These red dots here are the sampling locations for the 22 different samples we picked up on the Fissure 8 flow field when we went there in January of 2020. Of these 22 samples, 11 we were able to take to the MUX lab at the University of Missouri in Columbia, where we were able to get 3D computed tomography images of those samples. What you see here are 2D slices through those 3D images, and you can see that the light gray to white material here, this is actually the solid material of the samples, while the black and dark gray sections are either vesicles or the actual external portions of those samples. You can see that there is an overall trend towards denser material, less vesicular material, down towards the lava delta here, down at the far edge of the flow, and much more vesicular material close here to the vent. So there were a variety of vesicle shapes that we saw in these samples. I'll start with the subequant polygonal vesicles that we saw. These are large, almost geometric in shape vesicles on the order of 1 to 2 centimeters. These tend to be very frothy samples close to the vent. From here we saw collapsed polygonal meshes where they still retain some of the more large geometric shaped vesicles, but they are more deformed and more collapsed in their networks, even to the point of forming these more arcuate shapes that kind of nest into one another in this sample. Semi-spherical networks tend to be very, very small vesicles, much less than a centimeter, and they tend to form almost botryoidal clusters in the more spherical realm, whilst in these almost more square, more cubic in nature, they just form these large cubic segments in the sample. The stretched and torn vesicles tend to be more linear in nature and tend to form in these much more dense samples towards the end of the flow. So there is a rough vesicularity change with distance, but it isn't exact. You can see that closer to the vent, within the first 2 kilometers of the vent, you do get these much larger open vesicular pockets in your samples, whereas 4 to 10 kilometers from the vent, you tend to get more collapsed meshes. And then more than 12 kilometers from the vent, you do get these much more dense, less vesiculated samples. However, considering that all of these samples were taken from different lava types and lava styles, we got some that were from rubble down here on the lava delta and some that were from cores of flows, I decided that it would be good to compare those samples that were taken from the same type of structure. And so what you see here are the 7 samples that we took from the very external surface of Po'oi'oi overflows from the channel. Now you can see that there is some vesicularity decrease with distance, but it isn't exact. You've got these more dense samples here right close to the vent, and even some frothier samples further from the vent. So if you cluster these samples by vesicularity, then you can see that there's no real linear relationship with distance from the vent. These are all roughly 60% vesiculation, and they are anywhere from 1/4 of a kilometer to 6 kilometers from the vent. We've got this one at around 70% vesiculation, and then these 3 at around 80% vesiculation or greater. And so these, obviously you can't draw a linear relationship with distance from the vent, but you can in fact draw a relationship with the type of structure within the Po'oi'oi they came from. So these much more frothy samples, these very open, very vesicular samples, these ones that are greater than 80% vesicularity, they tend to be found in squeeze-up features, which are these very frothy linear features that occur between 2 plates of Po'oi'oi. And then they also form in these very frothy, very shelly Po'oi'oi ropes close into the vent. These more dense collapsed mesh samples tend to be from thicker po'o'i deposits. So you've got a thicker sheet flow here and thicker po'o'i toes. This is another sheet flow here, and then this is an amalgamation of different thick po'o'i sheet flows and toes. And finally, these more middling vesicularity samples came from a very, very thin, shelly po'o'i sheet flow that then ended up forming fabric-like folds around this obstruction along the channel. So in conclusion, there is a very rough vesicularity decrease as one moves from the vent to the end of the flow, as you can see here in the brightening of these micro CT images, as that indicates more dense material, less airspace. While there is that correlation between distance and vesicularity, it isn't exact. And so I was able to find that vesicularity also changes depending on the types of structures within the po'o'i flows, not simply just po'o'i versus a'a. So these very highly vesicular samples tended to come from squeeze-up features and very shelly po'o'i ropes, while these more dense samples tended to come from thicker sheet flows and po'o'i toes. And then the middling vesicularity sample came from a very shelly po'o'i and very thin sheet flows, so kind of a mixture between the two. So how does this relate to rheology? The vesicularity and vesicle shape actually have quite a substantial effect on the viscosity of a flow, and in large part this is due to the capillary number, where the capillary number is a dimensionless number, which is the relationship between the viscous forces of the fluid itself and the surface tension of whatever volatile is making up the bubbles in the fluid, or the vesicles in this case. And so as those vesicles become more deformed, that capillary number will increase, and this indicates a trend towards a shear thickening fluid, while low capillary numbers equal more spherical vesicles and shear thinning behavior. While we do expect to see a linear decrease with vesicularity and an increase with viscosity with distance from the vent, and we do rather roughly, there was a large variation in the shapes and sizes that we saw with distance from the vent, and this can be indicative of a variation in flow dynamics that were witnessed during this eruption. For more information on the rheology of these flows, please see this talk by my friend Janine Birnbaum, The Rheology of Three-Phase Lavas and Magmas. Thank you very much for your time, and if you have any questions, please let me know.